For problem set 5, you may want to get started a little bit early just because there are 5 problems in this set, and some of them are involved and require a little bit more thought. The first problem involves a multi-step process. It's got 1.2 moles of an ideal gas, and it's placed in a piston, and we're going to make a few changes on this. Now, the first thing we do is we lock the piston so the volume does not change. So in other words, we have delta V is equal to 0. So what kind of process is that? Okay, think about it because you'll need to invoke that as you do this problem. It's now going to be cooled at constant volume from 289 to 204 K, and you're to calculate the change in entropy. So essentially the main thing that's happening here is a change in temperature. All right, and you'll need to look for how do you calculate delta S when you have a change from T1 to T2 for a given process. Now, I think it might be helpful for you to draw a PV diagram, not just for this step, but for all of the steps in this problem to chart out where in the PV diagram this particular set of steps is occurring. In the second part, you're going to be setting the external pressure adjusted to match the internal pressure of this gas. And you're now going to insulate it from the surroundings. So you're going to slowly and reversibly increase the pressure so that you have an adiabatic contraction. Okay, so I want you to think about what does adiabatic process imply, all right? How do you calculate things for an adiabatic process? And in particular, you're going to be, again, calculating the change of entropy. You'll be returning to a final temperature of 289 K. So again, you want to know what does the adiabatic process say about a change in entropy. And then for part C, you want to add these two together. So if this is step 1 and this is step 2, then you want to find the total entropy for the changes in step 1 and the change in step 2. Now, as you do this, okay, you'll get different contributions from these two steps. I want you to think about what are the differences in the physical properties between these, between the starting point and the ending point. Okay, they're not going to be at the same point, so take a look at how they're different and see if you can understand how that justifies the result you get for the change, total change of entropy. All right, let's move on to the next problem. In this case, we're doing another thermal equilibrium problem. So we have two objects, A and B. So I'm going to use my standard diagram for thermal equilibrium stuff. So here's object A, here's object B. They're metals. They're going to be insulated from their surroundings. So we can't have any heat exchange with these two metal objects. In this case, they both have the same mass. Okay, so pay attention to that. And they're prepared at two different temperatures. So A is at 342, so it's the hot side, and B is at 293, so it's the cold side. And they're going to be allowed to reach thermal equilibrium, all right, and they have different heat capacities. So the specific heat capacity of A is given here. The specific heat capacity of B is given here. All right, so in other words, these two are going to have different heat capacities even though they have the same mass. So figure all that out. Remember what it means to reach thermal equilibrium. What has to change? How are these two sides related to one another when you undergo thermal equilibrium? And what is the condition at the end of thermal equilibrium? So you're obviously going to need to calculate the final temperature of this system, T final. And there is a practice problem in lesson, I believe it's 3B, that can help you with this process. It might be actually in 3A. Now, the entropy change for the system of two objects, this case, your total entropy change is going to be the change of the entropy in part A for metal object A and the change of the entropy for metal object B. Now, we talked about this also in a practice problem, so I will simply say that this is not going to be equal to 0 at the end of the process, okay? So what you want to do is evaluate using the standard formulas that we've given for the entropy change for a temperature change, because both of these are going to change temperature. They're changing temperatures from their initial temperature to their final temperature, which is given by T sub F. And you'll use this to evaluate these and ultimately get an overall entropy change for this particular process. All right, in problem 3, again we have a multi-step process, although you're given the PV diagram for this one. The 3 steps involved an isobaric contraction, an isothermal expansion, and an isochoric heating. So step 1 is this this horizontal piece across the top. Step 2 is this curved piece that goes from point B to point C, and step 3 is the vertical piece that goes from point C to point A. Now what you'll need to do is calculate delta S for each of these processes. So I want you to consider, for example, what are the considerations when you're calculating delta S for an isobaric process? What are the considerations when you're doing it for an isothermal process? And what are the considerations when you're doing it for an isochoric process? These are the 3 steps that are involved in this. Right, and so, since they are different, you'll get different values for this entropy change. Then, when you're done calculating it for each of these 3 steps, I want you to determine what the delta S is for the total change. Okay, and you might be able to predict that in advance without doing any calculation, but I'm going to let you work it through. And then, once you're done with that, these delta S's you should express as functions of the heat capacities as appropriate and the ideal gas constant. All right, and when you do this, when you calculate delta S total in the second part, you should express that in terms of CV, CP, and R. And in doing so, it should give you an idea of a relationship between these 3 quantities. All right, it's a relationship that is generally true in ideal gases, but this problem helps you demonstrate why it's true, or that it is true in this particular case. All right, in problem 4, we're going to look at a case where we're changing both the temperature and the volume and calculating delta S for that. So the top part is just really showing you how you get to a differential expression for ds. Okay, so this is a tool for you to use. All right, it provides you a means for evaluating entropy when you're simply going from one point on a phase diagram to another point, one pressure and temperature to another pressure and temperature. So in doing this, I think it's obvious that you will need to integrate ds from point 1 to point 2. And there are 2 different terms that contribute to this evaluation. All right, you're given a few of the specifics about the pressure at each point and the temperature at each point, and you're given also the constant pressure heat capacity, and that it's constant over this temperature range. So the whole idea is you're going to calculate delta S for this process, and it will be a means of using this information. So part of the trial of this particular problem is how do you use this information to actually calculate something that you need to calculate. I'll say that this one may generate some questions, but don't hesitate to send me questions if you have them. Finally, in the last problem, we have an interesting model here of a solid that's composed of 2 moles of diatomic molecules. So what I want you to think of is a set of diatomic molecules that are locked together in some kind of lattice, okay, and these molecules are all vibrating, okay, as diatomics, but these vibrations are, I'll just say, so fast that they're not necessarily contributing to the to the entropy that we want to evaluate, or to the entropy that we want to evaluate for this case. What we care more about is that if we treat each of these objects as though it were a frozen diatomic, and it has oscillations in between the molecules. So this is one molecule moving relative to another. We want to calculate first what the average energy is of this system at a particular temperature, and then the absolute entropy of this system. All right, so even though these are diatomics, we're almost going to treat them as though they were not diatomics, that they were just frozen objects that are vibrating relative to one another. They have a vibrational temperature that's given here, defined for you and given. This is actually very low for a vibrational temperature. Most vibrational temperatures are in the thousands, hundreds or thousands anyway. And here is an expression for the total system vibrational partition function, okay, which is going to be a little bit different because we are making an adjustment to the zero of energy for simplicity. Ordinarily, for a set of harmonic oscillators, you would have the first energy appears a little bit above the minimum of the well. So this would be at 1/2 h bar omega, for example, would be the energy of that first state. We're shifting the energy scale so that this corresponds to energy 0. Okay, that's all. These kinds of shifts of energy are basically done to simplify the math so that you can get to a cleaner result as you work through this. Okay, now in part A, where you're calculating the average energy, what tools do you have? Well, I've put a little hint up here. Average energy as a function of the system partition function. So think of the expressions that you've been given that express this average energy in terms of the partition function. That will be perhaps the best way to calculate the average energy in this particular case. And then you want to calculate the absolute energy, and there's a couple of ways you can do that. You can use the Gibbs expression or you can use the system partition function. They're both written down here at the bottom. The system partition function is a thing that we derived in one of the lessons, and so is the Gibbs expression. Note that in the Gibbs expression you will need to utilize an expression for the probability of being in the jth state. So obviously that will be something like e to the minus beta ej over the partition function. Okay, so use the one you like the best. I won't try to prejudice your results. I'll just say there's one that I prefer to use, and if you really have questions about it, isn't this a teaser? I'll let you know. All right, this is a little bit more challenging of a problem set, but you'll be able to, I think, really come to grips with a lot of the issues surrounding entropy, and especially statistical entropy through working through these problems. Good luck.